Speaker we have is Dr. Ahmad Javaid, from University of Toledo, and his presentation titled "Physical Layer Security Using Channel Estimation and Machine Learning." And Dr. Javaid received his B.Tech degree from Computer Engineering from Aligarh Muslim University, India, in 2008. His PhD from University of Toledo in 2015, along with prestigious University Fellowship Award. Previously, he also worked for 2 years as a scientist fellow in the Ministry of Science and Technology, Government of India. He's the founding director for Paul Hotmer Cybersecurity and Teaming Research Lab. He is currently an associate professor in the same department. His research expertise is in cybersecurity of drone networks, smartphones, wireless sensor networks, and other systems. He has extensively conducted research on human-machine teamings and applications of AI and machine learning to various areas. He has received funding for nearly close to 5.5 million in funding in wide varieties of agencies, including National Science Foundations, Air Force Research Lab, and NASA. It is my honor to welcome this distinguished guest, Dr. Javaid.
Thank you. Okay. Let's see if this, okay, it's working. Okay. Good morning again, everyone. And so compared to the first, two very interesting talks we had this morning, one on misinformation and the other one on, attacks on machine learning, this is going to be a very different presentation because, again, I'm going to go into a lot of details of how we applied machine learning to a specific problem domain. And again, I think many of you have, looked at many interesting posters as well, right? So this will probably look familiar to, some of those who are involved in similar kind of research. I'm going to talk a little bit about, communication security, how did we actually identify this particular problem. And we are going to talk about some of the experiments we did for, stationary transmitters and receivers, and then, some mobility transceivers. And then how did we use some of these techniques to detect some common attacks on cognitive and software-defined radios. And again, if time permits, I'm going to talk about some of the other machine learning related research that we are doing in our lab at the University of Toledo. This is again a quick brief about me, which I think Dr. Prakash has already detailed. So I'll probably just skip this and jump back to this particular model of computer networking, which we have been actually looking at for so many years, right? The OSI model, which has like 7 layers. Nowadays, we have switched to the TCP/IP model, which has become more popular and kind of compressed, right? So 4 layers, 5 layers of TCP/IP model. But it's still one thing which has remained the same is the physical layer at the very bottom, right? And again, I just pulled this up image, from the internet, essentially detailing some of the security mechanisms which are already in place at various layers, right? And again, nowadays, application presentation session, they're kind of combined together. It's just one layer right now. But it's still, there are a lot of other techniques at different layers which are available, over the internet, for secure message transmission and so on. But at the physical layer, there is definitely a lack of different techniques because again, physical layer is all about sending the signals, right? Whether it is a wired or wireless channel, we want to make sure that whatever signal we are sending is received on the other end. There has not been a lot of focus on ensuring security at that particular level. So this, you see again, that was one thing which was kind of strange to us, for decades actually, right? There has been actually some works in physical layer security in the recent years, and again, I'm going to kind of touch upon those as well. But again, in practice, there has not been actually a lot of focus. I mean, when we talk about Wi-Fi signals, for example, right? So then, the Wi-Fi signals, they have, some AES, level encryption, for passwords and things like that, but nothing actually implemented at the signal level. The signal itself will actually have only, the information which is coming, from the upper layers, right? So again, every layer, some end-to-end cryptography, right? Some cryptography at, application layer, at transport layer, at network layer, and so on, right? But, again, something is missing at the physical layer, right? We have some techniques for physical layer property-based key generation, and again, we can use them for authentication and encryption and so on without a lot of overhead. That was the whole idea, that we don't need the transmitter and receiver, both of them, to have a lot of computing power to generate these keys, because again, if you're going to use the physical layer parameters of the signals itself, the channel estimation, the noise and all those things, then you're not going to have a lot of computational overhead on the devices which are using these encryption techniques at the physical layer. And again, there are, the options are actually limitless, because, if you are generating keys using these physical properties, then you can use those keys to encrypt information at the upper layers as well. You don't necessarily need new keys for all these, other layers as well. So this is, again, just trying to what I just said is essentially the physical layer security versus computational security. So in the computational security, we basically give this task to the upper layers, right? The upper layers essentially secure the message with an encryption and pass it on to the physical layer. And they have separate keys. They are not generating keys using the physical layer properties. So what we want to do is we want to make sure that the physical layer can help in exchanging security keys. It can actually help in generating the security keys as well, again, using physical layer properties. And, it's a primary responsibility of communicating the signal reliably as well as securely, right? That's what, the transition we are looking at right now. And again, the most important thing is no computational assumptions, because if, again, you are generating these keys, based on, some specific parameters, then you don't have to do a lot of computation in generating keys on both parties. So some of the properties, which we have utilized, as I said, the wireless channel properties, right? So again, some of you who have done some work in communication systems, or at least students who have taken courses in data communications and wireless systems and so on, you probably know about these terms. Reciprocity, temporal variation, and spatial variation, right? So if there is a transmitter receiver pair at certain location, then the property of the channel between them will stay essentially this same from both sides, right? Irrespective of where they exactly are, right? Obviously, if there are location-based changes, if there are other environmental factors, changes, noise level changes, and things like that, then they will change. But given that the conditions remain exactly the same, and if you send signal from one side to the other and the other side to the first side, the channel properties will essentially remain the same theoretically. Obviously, in the real world, there are going to be some variance, right? We need to take that into account, and that's why we had to do some real world implementation and testing. What is that level of variance, and then based on that, we try to detect some attacks. So the two most important parameters that we used was carrier frequency offset and the channel impulse response. So again, quick description of these are given on the slide, but again, to understand it from the user point of view, again, who doesn't need to know a lot of details of how this is generated. So carrier frequency, when something is actually sent from one side to the other side, basically what's happening is on each side we have some oscillators which are oscillating at a certain frequency. So theoretically they can never exactly be the same, because there are always some differences when these are manufactured, again at the component level. So that difference will be essentially the carrier frequency offset. And then the impulse response is simply when you send something to a system, and whatever response it gives is basically the impulse response. In this case, when you send a wireless signal through a channel, whatever channel is responding with, that is the CIR. And again, going back to the communication system principles, we are right now talking about the most popular, one of the most popular techniques like OFDM, for example, orthogonal frequency division multiplexing, which has 64 subcarriers, right? And then within those 64 subcarriers, I believe 12 are used for the centering, and there are 4 blocks on one end and 6 blocks on one end and 5 blocks on one end, basically to ensure that there is no interference between the different channels. And I think 52 are actually used. So this chart here essentially is the plot of the channel impulse responses of 2 of these 52 channels. And I believe even after these 52 channels, 4 channels are still reserved for something else, and 48 are actually used for transmitting the data, right? But what we have done is we have used all those 52 channels, and we have just excluded those 12 channels. And again, this applies to even the Wi-Fi signal which we have right now, 802.11, ABGN standard essentially uses OFDM, right? 64 channels, spread out over 20 megahertz channel. I think each channel is 300 something kilohertz. Again, easy to look that up actually. So. And again, the motivation, right, why this needs to be done, right? Because again, there has been a lot of, attacks happening. And again, there are, definitely some assumptions. For example, if we look at, this key reinstallation attack, the crack vulnerability, which was, in the news a lot couple of years ago, one of the researcher was able to break the WPA2 encryption, not because of the weakness of the AES encryption algorithm, but because of the way the key was exchanged, right? You can actually use the WPS button, and then it sends a temporary key, and then you can generate AES keys and so on, right? So again, that was again related to again a very specific scenario. But if we were using something some property at the physical layer which which no one can actually replicate, then you might actually not have that problem, right? So again, as I said, we can use these physical layer properties to generate keys for other algorithms at different layers. So we can also use them to generate AES keys, for example. And what else? Yeah, so reduced overheads, enhanced complexity and stochasticity, because again, we are dealing with signals, natural phenomena, the noise and so on, and it's going to be actually really, really hard to replicate, that kind of stochasticity, right? I mean, when we talk about weather prediction, for example, right? I mean, all of us know, how, wrong it is all the time, right? You read in the news that, oh, it's going to rain today, and then it, rains probably like day after tomorrow, right? So again, and sometimes, it's just a difference of couple of hours, but again, it's very hard to predict and model these, natural complexities, right? So so we basically applied, some machine learning to see how this works. So this, this is another thing I wanted to point out. So this was part of, again a very big project which we did for Air Force Research Lab in coordination with the state of Ohio. And we, again, developed certain mechanisms for physical layer based key generation. We try to actually establish a upper bound on the key generation rate as well, because again, that is also important when you are trying to, reshuffle keys, generate new keys, at every instance and so on. And then the second part was the physical layer based authentication, which is what, which I'm talking about right now. The last part of the work was discriminatory channel estimation for link signature development. That was again, another detailed work which goes into too deep actually in the mass of the problem. So I'm not going to talk about those two aspects. Today we are only going to talk about this particular part. Again, application of machine learning to this particular area. Yeah, I can probably skip these, but yeah, this is again the same thing which I've been saying again and again, that if two, a pair of transmitter and receiver, they are at a fixed location, and the things between them are not changing a lot. Like for example, they are not moving, they are stationary. The environmental factors are the same. Then it is not amazingly difficult for the receiver to see if the two signals ST and ST plus T are coming from the same source. Again, using the physical layer parameters, right? CIR, CFO, and so on. And our assumption is that the attacker Eve is at some distance, at some distance, from the authentic or the original transmitter or receiver or both. The criteria which we have to again apply here is that the distance between these two should be greater than 1/4 of the wavelength, because what we noticed is that if the distance was closer, then there was the variance was very little, and it was very hard to distinguish whether it is coming from Alice or whether it is coming from Eve. So distance has to be a little bit longer, and I think from practical aspects it was I don't remember the exact length, but I think it was like 12 to 13 inches, something like that. So that's why, yeah, I think it's actually on one of the slides where we have described how much distance, it actually needs to be at a minimum. So yeah, so again, if the estimated 5-layer features from these two signals, have a small variance, then, they're coming from the same source. If not, then obviously there is a chance of spoofing or, some kind of attack. And again, in this work, when I'm talking about, these spoofing and so on, those are all at the signal level. We are not using these keys which are generated, for higher level, higher layer encryption in the TCP/IP or OSI model. So for the channel estimation, we essentially try to extract, 4 primary features from these signals, which is essentially mean, variance, and I think this is the skewness. And then the last one was I forgot the name of that particular feature. But again, using the signals, we extract these 4 features for each channel. And as I mentioned, there were 52 channels. So again, 4 features for each of these channels to get these features. And then we actually averaged all of these features over all those 52 channels. Finally, we got these 4 features for each of the signals. And I think we used like 1,000 OFDM samples. So for each sample, there will be unique features. For the CFO one, we calculated 3 types of channel frequency offsets, the coarse, fine, and residual. Again, if you see at the equation, again, these are pretty standard equations, for calculating the channel frequency offsets. So we collected this data again for the same number of OFDM samples. And then again, we tried to train machine learning classifiers, with these. I have the list of papers, where these are coming from. These are essentially 2 separate publications. The CIR-based one is a separate publication. The CFO one is a separate publication. And for the real-world experiments, we use this B210 ETIS devices, the software-defined radios, and the open-source, GNU radio platform, for all the design of, the transmitter, receiver, and data collection, and so on. So this is, one example of, the transceiver flow graph in the GNU radio software. And again, just trying to show here, I don't know if the image quality is that good, but I just wanted to zoom in and kind of show that, this is just one, the Wi-Fi, physical layer box. And this again, has so many things again going on. So yeah, if anyone wants to explore more, this is actually a very, very good platform, to again play with signals. When I actually did it, for the first time, I actually just used one of those examples, and I connected a very cheap SDR, which was like $35. I think it's called like SDR hash or something like that, and I was able to listen to like the radio signals like AM, FM, and everything. So again, very easy to use, and again very interesting to play with, if you want to use this particular open source software. So the first part was again stationary experiments. What we did was, this is kind of a map of the lab. It's a 600 square foot approximately lab, 25 feet by 24 feet. And the circles are essentially the chairs in the lab, and this is, was the setup. So basically, this is one of the receiver, and this green one is the transmitter, and the red one is the attacker. So attacker, as you can see, is very close to the original transmitter, essentially trying to to fake and become an attacker and show that, okay, I'm the real one. And there were again different instances, as you can see in this scenario. It was at a different location, kind of behind the original transmitter, and here it was kind of on a different direction and so on. I think there is another chart which shows all the location of the attacker based on the transmitter. Okay, so for the CIR we had 1,000 OFDM bursts, and for the CFO, okay, so for CFO we had 2,000 OFDM bursts. For this particular experimentation, for the indoor experimentation. And again, these will look very familiar, because most of these are essentially whatever we have in the Wi-Fi signal, the same parameters. Yeah, I can probably skip that as well, because I think most of you are have enough background in machine learning to know what are true positives to negatives, false positive, and so on. And again, ROC curves are a good measurement of how well a model is performing. So that's why we just plotted all the results using ROC curve and evaluated the area under the curve. And what you can see is like for some models, again, the results were like really close, almost equal to 1. Again, actually, it is equal to 1. And many of them were like 997, 984, and so on. So again, this really worked well, for certain classifiers. For some classifiers, for example, for decision tree, it did not, perform very well, especially when we use the CFO mechanisms. And for CIR, again, the top one you can see all were, perfectly classified. So this is, again, one reason many, machine learning experts and even communication system experts, they actually argue that we, shouldn't really be applying machine learning to communication because, again, everything is based on math, and, math can be really easily modeled using machine learning models, right? Because, again, machine learning is also math, right? But again, the point here is that we are also able to model other parameters which are introduced. For example, signals, again, noise. Noise are not actually based on any math, right? They are really stochastic, and it looks like, the model was able to model, that particular stochastic behavior. Again, some, more results, some records were misclassified when we used the CFO-based mechanism. For CIR, it worked really well. For CFO1, again, there were some issues. And for the mobility, you will see similar results. So we did both indoor and outdoor experimentation for mobility experiments as well. So this right here, I think, so this is actually the whole building. It's called the North Engineering Building at University of Toledo, which has all the labs. And these are essentially the corridors. So what we did was the students essentially used cards, and on the cards they placed these SDRs with their laptops and everything, and basically two students moved with those cards throughout the corridor. So obviously the distance between them were not accurate all the time, obviously. But again, it kind of did work. We had to actually set some thresholds for the error and so on. Similarly, for the outdoor experiments, to make sure that the transmitter and receiver at equidistance all the time, what we did was we used these magnetic mounts to attach these antennas to the front and back of the car. So let me zoom in again. So yeah, this B is essentially the receiver, and A is the transmitter, and as you can see, these are pretty close to each other, right? These two antennas in the back of the car. So yeah, the car was actually driving, in town. I think they drove on, a bunch of streets, nearby the university, and just to kind of, model how the transmission between these two, transmitter and this receivers are actually going to be affected due to environmental parameters, other signals and things like that. But again, the most important thing was that we wanted to make sure that the distance between transmitter and receiver stays constant, it stays same. Otherwise, again, physical parameters might change drastically based on the distance. So yeah, in the mobility one, it appeared that the CFO-based scheme worked better. In the previous one, if you notice, CIR mechanism worked better. So these are so these are the indoor and outdoor experimentation. So again, it's clear that indoor there was probably less interference, again environmental factors and so on. So the results were pretty good. But outdoor, it was again not exactly as the indoor, but still it was pretty good. I mean, if you can see, a lot of the AUC was almost close to 1, like 9.7, 9.8, 9.9. And again, some techniques, for example, decision tree, just like the last experimentation, didn't work that well compared to some of the other techniques. That was, again, the case for indoor and outdoor experiments. And okay, so the last part was detecting attacks when we, so these experimentations was just to see whether the model was able to learn, these behavior and or not, right? And again, you saw that, that Eve was there all the time, right? So that data was separately used to detect, the attack. And again, in the cognitive radio network, one of the most common attack, I think I have a separate slide for that, but in cognitive radio networks, we have a primary and secondary user. Typically, primary user is given, a priority because it is primary, right? Because of different factors. Sometimes primary user might have, paid more for the spectrum, so so they get priority over secondary users. And secondary users can only use the channel when primary users, vacate it, or there are no primary users, for example. Is the priority-based mechanism that is used, and second user has to vacate that channel if if a primary user comes back, and so on. So one of the most popular attacks in this is in this domain is primary user emulation attack, where a secondary user or an attacker, attacker who is a secondary user can try to pretend to be a primary user, and then it will kind of grab hold of the bandwidth. So again, senses if PU is idle and then injects the fake PU signal into the spectrum bank. Once that happens, the SUs will basically clear the channel, and then the PUE, the primary user emulator, the attacker will gain access to the spectrum, right? So we want to actually prevent that. So what we did was, again, yeah, this is the diagram I was referring to last time. So you can see the distance between the original transmitter and the attacker transmitter was always 12 inches. That's the minimum, for our experimentation that was required. If it was any closer than 12 inches, then, it would not be able to detect the attacker. Basically, the receiver will think that it is all coming from the same source. So again, to, do a little bit more testing, what we did was we used these different 8 positions for the attacker, the Eve transmitter, again kept around, and that's what, in one of the previous maps, if you saw different locations of Eve, that's what this was, it was trying to indicate. And the distance between the transmitter and the receiver was about 256.2 inches. Again, I have no idea how my students actually calculated this so accurately, but yeah, since it was in the lab, probably, it was easier to calculate this particular distance. And again, some channel responses, from different channels of the, or maybe, different transmissions, actually, yeah, different transmissions. These TX, yeah, all the red ones are from these red locations, E1 to E8, I believe. And then the green one is actually from the actual transmitter, which is supposed to be the genuine, transmitter. So again, you can visually see that each of these patterns is very different, and the pattern from the actual transmitter is very unique compared to all the other. It doesn't resemble the pattern, right? So again, here also we applied the same techniques, and as you can see, as we increased the number of OFDM bursts that was used to train the algorithm, the performance of algorithms definitely improved, and again, really good. Again, as you can see, like on the very right, the bottom axis, the x-axis is essentially the number of OFDM bursts which was used for training, and it really improved the performance of this signal. Yeah, this is what I was referring to in terms of a state of the art. So again, in the recent, the last decade, actually, a lot of people have started focusing on physical layer security and physical layer security based key generation for security of communication, signal communication, and many methods have achieved decent identification accuracy. For example, some of them have 85 to 90%, 96%. Again, 90%, and some Kalman filtered based CFO estimation that has given accuracy of 95% and 80% for SNR of 20 dB, and so the two different ones for two different SNRs essentially. So again, decent accuracy, and our method actually was was more accurate compared to many of these methods, and I think we had again these were published in these many conferences. And right now, the talk which we just had focused on these two particular papers, and out of those three phases which I mentioned earlier. So I think time-wise we are good, right? Yeah. Okay. So that's about it, for this particular talk. But again, I just wanted to show some of the people, who have been working in my lab, from the past couple of years. Again, I have a couple of students here as well, and some of these things, like for example, you can see we did a little bit of, again, as we were talking yesterday, right, where the money is, right? So a lot of, projects were essentially because of the same reason. And again, I was also personally interested in, exploring these areas. So a little bit of, again, robotics control, human-machine teaming, augmented reality, and this Android security. So again, Akshay here, for example, he's still continuing that work on Android security. This is a picture from a couple of years, I think probably 2018, I guess, that's when we had, a lot of students in my lab. And I think, oh, it's kind of hidden. So again, thank you very much for listening to this talk. And there's just a list of all the places we have received grants from, and collaborators and so on. I would like to put UND logo on this slide very soon if possible. So again, if you has any questions, please let me know. I literally breezed through these slides, again jumping very quickly because of the time limitations and so on. But yeah, if anyone has any questions, I'd love to answer them. Yeah.
Thank you very much for good work and good presentation. Actually, my question doesn't relate to your work. It's just for my curiosity. In the physical layer security, one of the conventional methods is to use the spread spectrum techniques, like direct sequence spread spectrum or frequency spread spectrum. So, these topics are hot those days for the physical layer security?
So, very interesting, good point, actually. You can probably take that mic. So, you can see here. Yeah. So, what you talked about was actually for reliability. The focus was that we want to transmit. I actually skipped that particular slide where I was talking about the traditional view of physical layer. The traditional view of physical layer was that we should be able to transmit the signal from one place to another in a secure, in a reliable manner. The point was that the signal should reach the other side, right? If there is, for example, jamming and all those things, then we can use, for example, a spectrum and so on. But there was not a lot of focus on security. And again, that holds true for almost anything we have designed, in the last, I don't know, 100, 200 years, right? The idea was essentially to get something, started, get working, and we never really thought about, the security aspects, right? And again, one other very good example is, when I was in my PhD, one of the reasons I started working on drone security was that I discovered this news about there was, some laptop discovered in Afghanistan, which had US drone feeds. And that's when the US military found out that their drone feed was not encrypted. And these terrorists were simply using, I think, a satellite TV software or something called SkyGrabber, which was Russian-made, incidentally, and they were able to grab the feed of UAVs, because it was not encrypted, so they were able to, see everything what a UAV was looking at, right? So it's a similar problem is actually here, right? When we don't have any, again, security mechanism at the physical layer, whoever grabs your signal will be able to record, right? I mean, again, at the higher level, we have more security, more encryption, like, AES and all that stuff, RSA and whatever, at the application layer. So in the end, they might not be able to see what is happening, right? But still, whatever you are sending at the physical layer, that information is still visible to them, right? So now what we are trying to do is we are trying to make sure that, first of all, we reduce the overhead for devices in terms of, generating their own keys, storing their own keys, and so on. I was actually looking at one of the posters regarding the biomedical device security. So, for example, when we have a pacemaker inside our hearts, right, we want to make sure that, we consume as little battery as possible and so on, right? So, we want to reduce the computational overhead on the devices itself, that are communicating.
Yeah, I just want to add that the spread spectrum techniques actually reduce the probability of the interception and also reduce the probability of the detection by unintended users.
Yeah,
So
yeah.
they are, very robust and strong techniques.
In the
Yeah.
interest of time, I'm going to make sure that we can have offline discussions.
Okay,
And
sure.
I'm just trying to see how to prepare for lunch and everything.
Okay.
Thank you so
thank
much,
you,
Dr.
everyone.
Ahmad. Appreciate it for your time. And so it's a small memento from us. Oh, thank you so much.